Hey there. Tonight we're going to talk about trig identities and proofs. So we spent some time during class today dealing with the identities, and we're going to talk about how to prove whether or not something is an identity. We'll start with a quick intro exercise, and there are 3 statements there, and it's asking you which of those 3 statements represents an identity, provide evidence to support your claim. If you were to be given a problem that asked if something was an identity, you could first check on the calculator to show that they were equivalent or not equivalent, and then you would have to actually show the proof algebraically. So today we're going to talk about how to show algebraically the proof. If we look at these first 3 statements, you probably recognize from our work today that number 1 is true. And number 2 is true based on the straightforward nature of the fact that you have 1 minus cosine equals 1 minus cosine. And I would suggest that this one is probably not true. So I might look at this graphically to kind of confirm, or I might think about what we know from transformations, right? If I were to write this as negative cosine theta plus 1, is that equal to cosine theta plus 1? Well, we know from our experience that the plus 1 is consistent, that the midlines would be the same, but the negative in front of the cosine indicates a reflection, so these two would not be equivalent, okay? We can use some of our transformation information for that, but some of the ones we're going to look at today are going to be a little more involved than just being able to say, oh, I can look at them and see that they're not equivalent based on what I know about the graphs or based on what I know about transformations. So any equation whose solution set is the set of all possible replacements for the variable known as an identity. So we know that from our experience with polynomials and from equations, that if you had 3x equals 3x, that would be true for all possible replacements of the variable. If you had 6 equals 6, we know that's an identity. So the same will be true for trig functions. If you had cosine theta equals cosine theta, that would be an identity. That would be true for all values. And from what we've been doing over the past couple of days, sine squared theta is equal to 1 minus cosine squared theta. That's an identity because that would be true for all values that we were to plug in. In order to actually prove an identity, you have to use logical steps to show that one side of the equation can be transformed into the other side of the equation using the already established identities. The Pythagorean identity, remember I said, would be very important. And then the other ones that we talked about in class today that we said would be really important are the reciprocal and the quotient identities, okay? In addition to our identities, we can also use properties of operation, and we can use some of our skills with adding and subtracting fractions, dealing with complex fractions. We're going to just today go through a couple of tips, and then we'll try one example, and then tomorrow we'll practice in class. It is, just as a note, is not correct to start with what you want to prove and work on both sides of the equation. So you absolutely cannot work on both sides of the equation, because if you modify both sides, then we don't really know if it matches our original, and I'll show you what I mean in just a moment. Okay, so some tips for proving or confirming that something is actually an identity. One of the major tips that I would offer is to start with the more complicated side. It's much easier to take something complicated and get it down to simpler terms than it is to take something simple and try to make it complicated. The next tip that I would offer is maybe change things into sines and cosines. I also talked about this today in class. I said that a lot of times I don't remember some of the other Pythagorean identities because I just turn things into sines and cosines, and you can make almost everything work by doing that. Another tip that might be helpful is that you might have to simplify complex fractions. Sometimes that can help. And we talked about ways to do that. So you could rewrite it as a division problem, and then you can use the multiply by reciprocal rule. You could multiply by the LCD. Okay, another tip might be to combine fractions. So maybe you need to add or subtract fractions. So you would need to have like denominators. As a math teacher, and most math teachers will probably agree with me, we usually really like trig proofs or trig confirmations because students are practicing all of the stuff that we've already talked about, adding and subtracting fractions, dealing with complex fractions, possibly even factoring. So sometimes you may need to factor. That might be a helpful or useful technique to try. Okay, if you need to, you can pause the video here and make sure you have all those tips. And then when you're ready, we'll start with an example. So exercise 2 asks us to confirm each identity. So some things I would ask you to do. I would ask you to draw down a line, and then we're only going to touch one side of the equation. Otherwise, we wouldn't really be doing a proof. I'm going to start with the more complicated side, which means that I'm just going to bring this side down because I don't want to touch it at all. I want it to stay that way. If I touch both sides, I don't really know if I've actually confirmed it because I could have made a mistake on one side and then made a mistake on the other, and they might not actually match. Okay, so I would take a look at this first one. I say, okay, sine, cotan. My goal is to turn sine theta times cotan theta into cosine theta. So that's my goal. Okay, let's see if we can do that by maybe following some of the tips. So I might change everything into sines and cosines, right? So cotan theta is the reciprocal of tangent, which means it's cosine theta over sine theta. And so that was actually pretty helpful because now any numerator can reduce to 1, cancel with any denominator, and so now I'm left with just a cosine theta. And they won't all be that easy to say, but that one is, we're going to start, of course, with something a little bit easier. So some of them might take one step like that. And just like when you took geometry, you might have, 10 steps. And some people might do the same problem in 3 steps that you take it to do in 5 steps. So it doesn't really matter as long as you're following appropriate mathematical rules. So as long as you're algebraically appropriate, it's fine to do it either way. Okay, I'm gonna ask you to try number 2 and probably number 4. We'll go ahead and do number 3 together. Okay, so again, we're gonna draw down that line and we're gonna start with the more complicated side. So I'm gonna think about my goal. My goal is to get a cosecant squared theta. Okay. All right, so if I'm not sure what to do, I might just start changing things to sines and cosines. So cotangent would be cosine theta over sine theta. I'm just going to do the division piece of this in one step. So I'm really just writing that divided by tangent, and I'm going to rewrite tangent as sine theta over cosine theta. And then I still have my plus 1. So I'm just taking this fraction, cotan theta, divided by tan theta, and I'm rewriting it in terms of sines and cosines and rewriting it as a division problem, which is technically what a fraction is, right? Okay, so now if I have a fraction divided by a fraction, I really have a fraction, keep, times the reciprocal. So keep, change, flip, if you will. Okay, so now in my numerator, I have cosine squared theta. Denominator is sine squared theta plus 1. Okay, so now remember, our goal is to get to cosecant squared, all right, which means that I need essentially 1 over sine squared. Well, now I have a fraction, cosine squared theta divided by sine squared theta, plus a 1. I can rewrite 1 as a fraction, right? I can rewrite 1 as sine squared theta over sine squared theta. Now, since my denominators are alike, I can go ahead and combine the numerators. Hopefully you're writing a little bit smaller than me so you can fit it in there, okay? And so then if we use our Pythagorean identity, cosine squared theta plus sine squared theta is really 1. So this is equivalent to 1 over sine squared theta, and 1 over sine squared theta is equivalent to cosecant squared theta, which is our goal. We wanted to get to cosecant squared theta, okay? So maybe for some of you, you skipped the blue step to the black step. Maybe you left, instead of doing the black step, you just rewrote over 1 sine squared theta over sine squared theta. And so you might have been able to kind of fit yours on here a little better than maybe I was. So maybe you made that there, then you had this step, then you had this step, and then you had lastly your cosecant squared theta, okay? So one thing we can say is that typically you will need a decent amount of space for some of the proofs, whereas others you might not need much space at all. And the idea is that we want to get from the more complicated side to the easy side. Okay, so I'd like you to try 2 and 4, and we will practice tomorrow during class.